Hello, and welcome back to the Taurus Report, the bull in the china shop of cosmology. I would like to begin today by just summing up what we've covered so far. I explained that gravity is actually caused by trillions upon trillions of oscillations within the nuclei of atoms. Because the nuclei contain charges, and because the space of a nucleus is very constrained, we can sort of describe the motion as an oscillation back and forth of charges. And there's trillions and trillions of these going on at the same time. And for the most part, because you have these trillions of oscillations, for the most part they're unrelated, and it's going to have an effect of nothing, just random noise. But as I explained in the previous video, the electromagnetic force is so many trillions upon trillions upon trillions upon trillions of times stronger than what we call the gravitational force. All you would need is some tiny microscopic quantity of these oscillations to be in sync, and the synchronization would have to be both in the sense of time but also space, so that the effect is a summative, sometimes attractive effect, and sometimes repulsive effect. Now, because this is what creates gravity, it is still going to be dependent on distance, meaning that over a large distance, the power of this force is going to decrease, and so you are going to see it sloping downward. I want to emphasize that by showing this graph from my paper. Now again, to access my paper, for any of you that don't know, if you open up a Google tab and just type in Taurus Report, all as one word, .com, and press enter, it will bring you to my site. And here, if you scroll down, you can access my paper on cyclic gravity and cosmology. You can also listen to the Taurus Report on Spotify, see all of the videos in a playlist on YouTube, or if you have Facebook, there's also a playlist on Facebook. But in any case, my paper is here. And if we scroll down here, we can see that I am saying, notice how, like, this blue line is a graph of gravitational force according to CGC, and notice it does decrease with distance, but it does have unpredictable little squiggles and stuff in it. And this is for our solar system, a proposed possibility. I'm not claiming that gravity in our solar system actually conforms to this. I'm just saying that with CGC, we can get all kinds of different possible expressions of the gravitational force that do decrease with distance. But these various expressions of the gravitational force are practically infinite, because I am portraying the gravitational force as a sum of waves whose power roughly decreases with distance. But notice sometimes you can have little, slight increases or decreases faster than expected, etc., etc. Now, I would like to share with you something I found at the University of Connecticut website, and I will put all of the links that I referred to in this presentation. I will put them in the comments for each video that you're watching. So if you have some sort of waveform and you add those waves together, it will give you some other form. Like these two here added together give you this large waveform because they're kind of in sync. And then these two added together, if you add them together, because they're kind of canceling each other out, you get a flat line. And my point here is when you add waveforms together, you are going to get some other form that might be a wave, but then it might not be a wave. And basically, you can get any kind of form that you can imagine. And so it makes perfect sense that you can get strange forms like this, because I am claiming that gravity is, in essence, a sum of trillions and trillions of oscillations. And this sum can appear differently in different contexts. And one of the things that can happen is there are certain contexts in which gravity can actually be negative. It can actually be repulsive. And so what does this mean long term? For one thing, macro bodies like stars and their planets orbiting them, after being in an interaction for billions of years, they would become acclimated to each other, and there'd be a strong tendency towards circularization of orbits for macro objects like planets. And this is because at certain distances, gravity would be weak or repulsive, and at certain other distances, gravity would be at its max. And each object over billions of years would tend to be pushed and pulled and end up in a place where it is orbiting in a stable, roughly circular orbit. So I am claiming that systems start out sort of how I depict H.L. Torrey system here in my paper, scrolling all the way down to the end here. Again, this is a picture of H.L. Torrey, and I'm claiming when systems are being born, initially, all of the different gas and matter is not acclimated, and so because it's not acclimated, you end up with areas of repulsion around the central object, either repulsion or else very weak gravity, and I'm claiming that that's what these dark rings are. And all of the matter would tend to conglomerate into places where the bright rings are, and that would form the planets. And so over time, systems would become acclimated, and you end up with these sort of stable orbits. And so this presents a very interesting picture. What does this mean for astronomy and astrophysics? What this means is that for quite a while, in my opinion, it will be very difficult to come up with a gravitational force law that is elegant and simple and consistent at all scales and in all contexts. At the current time, I am saying that is impossible. And so instead what should be done is that we admit gravity depends upon the local context. It depends upon the scale you're talking about. And we cannot come up with a general, simple, elegant force law for the reasons I've outlined. And what that means for cosmology and astrophysics is we should temporarily give up on trying to do that and instead move towards an approximate force law where we are just saying, okay, things in this context and at this scale, at this place and time, they seem to be moving like this. And you come up with a sort of ad hoc equation to describe that movement for that specific context and that specific scale. So you could have an equation like, for instance, the way most planets behave in our solar system. And then you might have to make an ad hoc adjustment for Mercury. Things like that. You'd have to come up with an ad hoc force law for galactic rotation rates. And I'd like to sidestep to that for a minute, looking at galactic rotation rates, because Galactic rotation rates is the context in which astrophysicists first started questioning general relativity and saying, do we need a new force law or do we have to come up with something else? And most theorists have adopted the LCDM, which incorporates dark matter, which I disagree with. But a subgroup of theorists called MOND, that was initiated by Moti Milgram and is also subscribed to by such luminaries as Pavel Kraupa and Stacy McGaugh, etc. And I would like to share a video with you, again, well, a portion of a video. It's quite long, so I'm not going to share the whole thing. But a portion of this video put up by Pavel Kraupa, he's an astrophysicist in Germany, where he discussed a lot of, in the context of galactic rotation rates, he discussed a lot of this with other theorists. And the main thing I'd just like to point out right now is if you go in this video, and I'll put the link in the comments again, if you go in this video to almost exactly at the 1 hour point, like 1 hour and 10 seconds or whatever, he puts up this very interesting visual graph where MOND, which is modified Newtonian dynamics, where this is a modified gravity approach that does away with dark matter altogether. And it predicts galactic rotation rates very well. Here we have a graph of, and the dots here, and I'm looking at this graph right here. Okay, the dots here represent data points, which is the velocity of stars, in this particular galaxy. And then the line is the prediction according to MOND. This is a modified Newtonian dynamics model subscribed to by like Dr. Milgram and Stacy McGaugh and others. And notice how well it predicts the data points, even including, as Dr. Kraupa points out, even including these little squiggles here. And LCDM cannot do that for galactic rotation rates. And for me, this is absolute proof, in my opinion. It just absolutely disproves a dark matter explanation for galactic rotation rates. Okay, if you can predict that line so well, where it incorporates even those little deviations like that, and your model predicts it perfectly, and MOND does that for galactic rotation rates, to me that just disproves dark matter right there. And what it shows, now I disagree with MOND, and I'll get into that, okay? Not in this context, because I think they've proven their point in this specific context. So I don't disagree with them here on galactic rotation rates in the sense that I agree with MOND 100% that for galactic rotation rates, the gravity force law in that context matches what they're saying, okay? And what does that mean? That means that the gravitational force law is utterly, completely, demonstrably dependent upon visible, known types of matter. Their force law that captures all those squiggles is based strictly on what we can see in that context. And in that sense, I agree with them. And since I am kind of cheating a little bit because I am embracing ad-hocness, right? I'm giving up on an elegant, simple force law for the reasons I've already outlined. And I'm embracing ad-hocness, where I say, okay, in any specific context, we just look at how objects are moving and we say, okay, in that context, at this time and in this place, gravity is behaving like this. And for galactic rotation rates, MOND does a very good job with that. Now, the way in which I disagree with MOND is when you leave that context of galactic rotation rates, I think Mond has problems, because if you're trying to build an overarching theory that explains everything in the sense of what about cosmological expansion, what about what we're seeing with the Webb telescope, although I have to admit Mond has some good answers for some of that as well. But I don't think Mond addresses cosmological expansion at all. Doesn't say anything wrong, it just isn't speaking to that issue. And I think that if you're going to, that cosmology requires you to try to come up with an explanation for all of cosmology. And so while I embrace Mond in its ad hoc treatment of galactic rotation rates, I feel that it doesn't address other things that need to be addressed in cosmology, notably cosmological expansion, and I would like to move to that next. In my paper, I have a section about galactic rotation rates that discusses what we just talked about as far as those things, and gives a graph. Here is a plot of the velocity of some stars in a galaxy, and then what would be predicted by a form of CGC. And again, I have to admit it's an ad hoc form, so it is data fitting, but I believe that I'm explaining in a very convincing way why we have to use data fitting, because coming up with an actual simple and elegant force law, in my opinion, at this time is not possible. So data fitting is the only choice we really have right now. Now, moving into cosmological expansion, we can kind of do the same thing sort of in a different way. The problem with cosmological expansion is we're talking about repulsion, because most distant galaxies, when we look out into the universe, they appear to be accelerating away from each other. And so if we're going to blame all motions on gravity, that we're seeing all of these macro motions, then we would have to say that galaxies must be, a lot of them, pushing against each other, and so gravity at those contexts and in those scales is actually repulsive. So I look at some different scales here, and this graph in my paper here, this is a graph of the velocity if something was orbiting, which is not really, it's not really a good explanation when you're talking about intergalactic stuff, because like galaxy clusters are not really like orbiting each other, okay? But I use this as if they were, okay? So this graph, this yellow line here, would be the orbital velocity if they were orbiting at that distance. If they were orbiting at that distance, what would their orbital velocity be? Now, this zone that I've encapsulated with these two green lines, this is the zone inhabited by the size of most galaxy clusters. Okay, when you're talking about clusters of galaxies that seem to be gravitationally bound. So we see a positive velocity if they were orbiting each other, even though they're not. You would still get this result. I'm treating them as if they were. Now, what does that mean out in this zone? Okay, here acceleration becomes negative, meaning that out in this zone where you see nothing, it means that gravity would actually be repulsive in this zone. And that's why there is no orbital velocity, because orbiting would be impossible where gravity is repulsive. And so there's no orbital velocity out here, because in this zone, gravity is repulsive. And so this would explain why most galaxies, when we look out into the universe, why most of them are accelerating away from each other. It's just that gravity is repulsive at that scale. Now, I need to make a couple of comments about that. So let me make a few comments about that. Comment number one, as I shared in a previous video, in my opinion, not all of the redshift is due to galaxies accelerating away from each other. I think some of the redshift is due to what is called tired light. All this means is that as light travels these huge distances, intergalactic distances, it loses some of its energy to the medium it's passing through, and so it becomes slightly redshift. Now, various astrophysicists have proven, in my opinion, that all of the redshift cannot possibly, maybe not even most of it, all of the redshift cannot be due to tired light. Okay, that has been proven by various methods, which I'm not going to get into, but I've looked at it, and I am convinced that tired light cannot explain all of the redshift. So I am just claiming that tired light is responsible for a portion of the redshift. At a minimum, tired light is responsible for that portion that would require faster than light travel, because according to CGC, nothing can go faster than light, while in general relativity, it is kind of acceptable to have faster than light if that overage, I'll call it, is due to cosmological expansion. Well, CGC says no. There is no cosmological expansion in CGC, and so there cannot be anything that travels faster than light. So if some of the stretching, the redshifting, seems to imply faster than light motion, then the portion of that redshift that is over that speed of light barrier must be due to tired light, according to CGC. So that is the first comment I wanted to make about the tired light hypothesis. The second comment I want to make, I'll get to next. Because standard cosmology assumes stretching of space, which they got from Einstein's general relativity. Because that is assumed, and if you assume that that stays approximately constant, for all of cosmological history, if one assumes that, then as you extrapolate back in time, the universe would get more and more compact and get hotter and hotter, until finally, if you extrapolate back in time, you end up at a very hot, dense place that we call the Big Bang. Now, I am disagreeing with all of that. I am saying that the expansion is not due to the stretching of space, and instead, it is because gravity is this waveform I've described thus far. This means that at certain scales you're going to have repulsion, and at other scales you'll have contraction, and it is very likely that the universe has been, and I'm going to say gently, I'm going to use the word gently to contrast with the word bang, okay? In my opinion, the universe has been gently expanding and contracting eternally. It has been going like that forever. Now, in this present era, if we extrapolate back, I agree that as we look back some billions of years, we will see a denser universe. I won't call it a Big Bang because, in my opinion, we will always see, forever, no matter how far back we look back, we will always see stars and galaxies. Now, when the universe is in a more compact phase, those stars and galaxies may look different than they do now. In other words, things might not look exactly like they do now, so there might be differences in how things look, but we will see stars and galaxies, with some mild, well, I don't know if I should use the word mild, but with some substantial differences, but the universe kind of looking like it does now. And then, assumably, I don't know if that's a word, but I assume that at some point, the universe will expand to a point and it will reach some maximum, and then it will start contracting again kind of gently until it gets to a point where it becomes repulsive, and then it starts expanding again. And so I'm claiming the universe is in this endless cycle of gentle expansion and contraction forever. Now I would like to discuss what I am going to be taking a look at next week, because in my opinion it is one of the central parts of my theory, and in my opinion the most exciting, because it lends itself to some ways of proving or disproving both general relativity and CGC. There are some experiments that can be done to prove or disprove either one, and I will share those in the next episode. But what I am going to be looking at is this. General relativity was adopted because it makes some very powerful predictions that turned out to be true. I would like to list those. The first prediction that I'm going to talk about, and I will go into explanations of these according to CGC next week, but Einstein predicted that light would be deflected by a large angle by the sun's gravity indirectly, because according to general relativity, large masses like the sun warp space, and so then light, if this is the sun, then light would be bent as it passes the sun because space itself is warped. Now in CGC, that is not the case. There is no warping of space, and so CGC must also predict this deflection of light. So that is one prediction of general relativity that has to be dealt with. The second prediction of general relativity that has been confirmed in countless experiments is time dilation. The fact that time slows in two different contexts. One of them is in a near a large mass or a high source of gravity, like the sun. As you get closer to the sun, time dilates, or even the Earth. We know this because of the way we have to synchronize our satellites. So general relativity predicts the slowing down of time. And it does this with geometry, kind of treating time as a dimension of space. And just as gravity warps space, it also warps time, because time is also a continuum. Now under CGC, that is not the case. Okay, time is not a continuum. It should not be treated as a dimension of space. But then CGC must also explain time dilation and also predict it. And I will share how CGC does that next week. The last major prediction of general relativity has to do with the increase of momentum at velocity. Basically, it's as if an object has more mass the faster it travels relative to another object. And so, again, Einstein dealt with this by linking mass to geometry. So if an object has a high velocity, it also has a high mass. I mean, not strictly speaking a higher mass. It's actually a higher momentum. But for a layman, we can say it's heavier. It's a higher mass. And so CGC must also predict this, which it does. And so in the next episode, I am going to jump into both special and general relativity and address and explain how CGC also predicts these things in a way that does not require the deformation of space. Thank you very much for watching the Torus Report this week, and we will see you next week. Bye-bye for now.